Hi everyone, this is Ms. Patel Dane here. So we're going to talk about topic 7.3, reaction quotient equilibrium constant, topic 7.4, calculate the equilibrium constant, and topic 7.5, the magnitude of the equilibrium constant. So these are the learning objectives from College Board. But by the end of this lesson, you will write equilibrium expressions using K or Q, determine what it means when K or Q are less than 1 or greater than 1, calculate K or Q given different pressures or concentrations, and then explain the relationships between K and Q. So first, we're going to start off with an equation called the Haber process. The Haber process is one of the most important reactions that we have on our planet. It makes fertilizer from gaseous nitrogen and hydrogen. So, given 0.4 atmospheres of nitrogen, 1.2 atmospheres of hydrogen, and 0.4 atmospheres of ammonium gas for the unbalanced chemical reaction representing the Haber process. So I'm going to have you balance the equation, show the equation in terms of rates at equilibrium for the different pressures, rearrange the equation to solve for the rate constant of the forward reaction over the rate constant of the reverse reaction, then replace the rate constants with the equilibrium constant, Kp, and then solve for Kp. It seems a bit tough right now, but let's go through it. So I'm going to have you pause first just to make sure you get this information down. All right, so when we're going through this, we need to first balance the chemical equation. So when we do that, we're going to add a coefficient of 3 in front of the H2 and a 2 in front of the NH3. Then we're going to show the equation in terms of rates at equilibrium for concentrations. So essentially, we're going to say the rate of the forward reaction is going to be equal to the rate of the reverse reaction since the system is at equilibrium. We're going to use the small k for the rate constant and F for the forward. And that's going to be multiplied by the reactants, N2 times H2, and then we're going to take the coefficient and raise that up to a power. So it's going to be H2 cubed. We're going to set that equal to the rate constant of the reverse reaction and the products. So NH3, and we're going to square that because it has a coefficient of 2. Then we're going to rearrange for the rate constant of the forward reaction over the rate constant of the reverse reaction. So we have to divide both sides by Kr, and then divide both sides by the reactants to get to cancel out the N2 and H2. So again, we're going to divide N2 times H2 cubed by both sides. So then when we rearrange it, we're going to have the rate constant of the forward reaction divided by the rate constant of the reverse reaction set equal to the product, which is NH3 squared, over the reactants, which is N2 times H2 to the cube. Then we're going to replace the Kf and the Kr with the equilibrium constant, or Kp. We're using P because this is in pressure. So since this is in pressure, we're going to rewrite the reactants and products in terms of pressure. So we're going to use a capital P and then use a subscript for the products and the reactants. We're still going to keep the 3 and the 2 there. Now we're going to solve for Kp and plug in the values. So we have 0.40 atm of nitrogen, 1.2 atm of hydrogen, and 0.4 atm of ammonium gas. So we're taking the pressure of NH3, the ammonium, so it's 0.4 squared, divided by the pressure of N2, which is also 0.4, times the pressure of hydrogen, or H2, and that's to 1.2. Now, since we have 0.4 on both the numerator and the denominator, I'm going to at least cancel out one of them. So as we solve for this, we have 0.4 divided by 1.2 cubed. And that is going to be equal to 0.23. So that's how we solve for Kp. So basically the rules as we go through this. When we write a general expression in terms of K, the equilibrium constant, note that this is capital K as well. We're going to say it's the products over the reactants. And then we raise each of the products and the reactants by their coefficient. So the little n represents the number of moles of each substance. Of course, the coefficients get raised up to exponents, hence why you have to balance the chemical equation first. And when we're thinking about states of matter, so we have to think about pressure or concentration. Solids and liquids do not change very much in terms of pressure and concentration. Actually, not at all for pressure. And so we don't include any of them in the equilibrium expression. We do, however, include any gaseous or aqueous solutions. So the units of K, we actually didn't have any units of K. They end up getting canceled out, and it is a unitless number. So when K is greater than 1, we know that the numerator is bigger than the denominator, so that the products are going to be favored, or the reaction tends to go more towards the products, or the forward direction. When K is less than 1, we know that it's actually going to go towards the reverse reaction. So the reactions are favored, and the reverse direction is favored. So we have different types of Ks and Qs that you'll see, and we'll talk about Q in just a bit. So we talked about Kp, which was the equilibrium constant in terms of pressure, but we also have Kc. Kc is the equilibrium constant in terms of concentration. That's when you have an aqueous solution, or even sometimes some gaseous substances as well. It's always going to be in molarity, or given to you in terms of molarity, and that's when we use the brackets instead of the parentheses that we've seen before. Kp, of course, is pressure, and then we use capital P, subscript, whatever the substances are. Keq is just a general term for at equilibrium. Ksp, which is what we're going to visit later on in this unit, is the solubility product. So when we have substances going from a solid to an aqueous solution, or dissolving. Ka is equilibrium constant in terms of acids, or for acids. Kb is for bases, and Kw is for water. We'll visit these last three in Unit 8. So Q. Q means whenever the system, or the reaction quotient, whenever the system is not at equilibrium. So it's pretty much any other time besides equilibrium. For equilibrium, we're going to use K. When it's not at equilibrium, we'll use Q. So here's another practice problem. We're assuming that the concentrations of the following can be measured for the following reaction at any moment of time. So we have iron plus 3 plus thiocyanate ion is in equilibrium with iron thiocyanate, and the equilibrium constant for this, the Kc, is 40. So first we're going to balance the chemical equation, then write out the equilibrium expression. So the products divided by the reactants, and then we're going to raise any of the products and reactants by their coefficient. And then we're going to test to see what the constant is going to be at these three conditions for A, B, and C. So I'm going to have you pause at this point and go ahead and get started. All right, so as we go through this, we balance the chemical equation first, and both sides are balanced. So then we're going to go ahead into the equilibrium expression. Since K was given to us in terms of Kc, we're going to go ahead and use Kc as well. So we have FeSCN plus 2, and we're going to put those in brackets because it is in concentration as opposed to P, and divided by the reactants, which is Fe plus 3, and SCN minus 1, again, both in brackets. There are no coefficients, so everything's just assumed to be raised to the first power. Then we're going to determine solve for Q for each one of these, and then determine whether the reaction's at equilibrium. So for the first one, QC is equal to, again, the products over the reactants, and everything is, in this case, everything is 0.010 molar. So we're going to use the brackets to represent that molarity. So we have the product 0.010 divided by the reactants 0.10 times 0.10. And since we have 0.10 on both the numerator and denominator, we can cancel out at least one of them and make the top or the numerator 1. So then we type in 1 divided by 0.1, and that's equal to 100. So the Q is going to be 100, and the Kc, which we've seen before, is going to be equal to 40. So since 100 is greater than 40, we can see that QC is going to be greater than Kc, and we'll talk about what that actually means in a little bit. If you need to pause the video to continue on the rest of this, feel free to, but if not, keep going with us. So for the next one, the products, the FeSCN plus 2 was 0.30, then it's divided by the reactants, which are 0.10 times 0.15. We can't cancel anything, but we can at least plug in our information. When we get this, we see that QC is equal to 20. So we have QC, and then we're going to again compare that to KC, which is equal to 40. So in this case, the KC is going to be greater than the QC. So the system at equilibrium is going to be greater than that not at equilibrium. We'll do the same thing for the last problem. So the top is 0.10 molar divided by the 0.050 times another 0.50 0 when we plug this in. And don't forget the parentheses for the denominator as well. We end up seeing that QC is equal to 40, which is going to be the same thing as your KC. So they're both going to be equal. So for this next part, if Q is greater than K, that means that the reaction is going to proceed in a certain direction, either forward or reverse, and favor either the reactants or products. So if we think about it, Q and K are both mean that we have the products over the reactants. But if Q is greater than K, that means that the numerator must have been bigger for Q than it was for K. So it means that the products is going to be a larger amount than the reactants. In order to get this to equilibrium, we need to shift this or move it to the reverse reaction to favor the reactants so that we have Q equaling K. The opposite, Q is less than K, we end up seeing that the reactants are going to be larger for Q. So therefore, we're going to shift this reaction towards the product or towards the forward reaction. If K is equal to Q, then we know the reaction's at equilibrium. So this was the work that we just did. Go ahead and label each one of these in terms of which one is going to favor the forward versus the reverse reactions. So pause here and go ahead and do that. So we can see that for the first one, since QC was greater than KC, this is going to favor the reverse reaction so that the system not at equilibrium will, again, go towards a reverse reaction so it can then establish equilibrium or kind of get to that KC value. For the next one, we're going to see it's going to go in the forward reaction, again, to reach whatever the equilibrium constant is for K. And then for the last one, it's at equilibrium, so nothing changes. So for this part, we have, this part actually is not tested numerically or quantitatively on your AP exam, but I do want you to see it in case you see it on any old free responses. We can convert between Kc and Kp. Kc, of course, is equilibrium concentration at equilibrium, and the equilibrium concentration in terms of pressure for Kp. So we have to multiply the Kc times the times RT and then delta N. So if we think about this, the Kc is the equilibrium constant in terms of concentration times R. We've seen R before when it comes to gases. That's on your reference table. It's equal to 0.08206. Your T, since we're dealing with gases, has to be in Kelvin as well. Your delta N means that you have your number of moles or the change in the number of moles. So it's essentially the moles of the products minus the moles of the reactants. So go ahead and pause this one and do the equation that we had for the ammonium, the first example that we had. All right, as we go through, we're going to write down our equation just to remind you. We have N2 plus 3H2 is at equilibrium with 2NH3. So we found earlier that our Kp, or we found the Kp value. So now we're going to solve for Kc. So we want to divide both sides by RT raised to the delta N in order to cancel out both sides, or cancel out the right-hand side. All right, so again, we've got Kc is equal to Kp over R times T, and the product is raised to the change in the number of moles. So now we can plug in our values. We found Kp before to be 0.23, and then we know R is 0.08206, and our T is 298 Kelvin. Now to find our delta N, we want to take our moles of our products. In this case, we have 2 moles of our products minus the moles of our reactants. So we have a total of 4 moles of our reactants, because don't forget we have the imaginary 1 in front of that N2. So that leads us to a -2. So we'll go ahead and type that in. 0.23 divided by the R value times 298 raised to the -2 power. We should have gotten 137.538. So when we think about, go through and figure out what Kc is, it is 137. So at this point, can you write the equilibrium expressions using K or Q? Can you determine what it means when K or Q are less than 1 or greater than 1? Can you calculate K or Q given pressures or concentrations, and then explain the relationships between K and Q? Thank you very much and have a great day.